Okay, so why don't we take a look at the first and simplest solution to busy waiting, and that's called a lock variable. All right, so let's why don't we grab this code here? It's certainly gotten quite busy, but let me see if I can grab this. Yeah, let's try it. I'll clean it up. Copy that, and I'll bring it down here. Paste it. So we can just kind of look at our critical section, clean it up a little bit. Okay, so we know that the first line is not part of our critical section, but the rest of it is. So I'm just going to move this down here a little bit. And what I want to do is just write some code that will protect this critical section. All right, so the way I'm going to do this is with a lock variable. All right, so what I'll do here is I'm just going to write a while loop right here. I'm going to say while lock is not equal to 0, and I'm going to put a semicolon here. So that's a really tight loop. It's just going to run over and over and over again until lock is not equal to 0 anymore. All right, and when lock is not equal to 0, what we're going to do is set lock equal to 1. And what this means is now we have the lock. Okay. So when lock is 0, it means that there is no process running that wants the critical section, all right? That wants the lock essentially. But if lock is 1, okay, if we're running here and lock is 1, it means that there is another process that is currently in the critical section and then we need to wait, okay? So let's continue here. While we have the lock, we can execute this code here, and this is our critical section. When we're done with the critical section, we're just going to set lock equal to 0. All right, now lock is 0, and so some other process can go and use the critical section, and then we can go back up here and we can wait for the next file to print. Now, I want to show you this with two processes side by side. So I'm going to shrink this bad boy down a little bit, maybe a little bit bigger, and then I'm going to make a copy of it. Looks like I lost that. Okay, I'll make a copy. We'll paste it here. And so we can have kind of like a process A and a process B sitting next to each other. Okay, now, does this work? All right, it looks good, right? Process A is running. You know, we'd initialize lock to 0 somewhere, and process A is running, and process B is running. Process A says, "Oh, I see that lock is 0, so I'm going to grab the lock and set it equal to 1." Now over here on the other side, process B is running, and it says, "Oh, looks like lock is not 0 right now. Someone else has got the lock." So then process A gets a chance to run, and it'll reset lock to 0, and then process B, seeing that lock is now 0, will get to run, grab the lock, and then reset it to 1. So reset it to 0 when it's done. So it does look pretty good. It looks like this lock variable is protecting the critical region that is the print queue. Or is it? Because Houston, we do have a problem here. All right, we actually have another race condition. And the race condition involves lock itself. Because do we have a shared read write? Not the print queue, but lock itself. Lock is shared, and it's read write. It's a read write variable. So because it's shared and it's read write, and because PA and PB are concurrent, we have a race condition on lock. All right, how could that play out? How could that race condition on lock play out? Well, let me show you using another color. All right, so step one, we wait for a file to print, and process B does the same thing. Step two, we begin to spin on while lock is not equal to 0, but process B does the same exact thing. All right, the current value of lock is 0. So process A says, okay, lock is 0. I can move from the while loop and I can start to execute this statement, lock is equal to 1. But you see, at the same time, process B sees that lock is 0. So it says, oh, I can move to lock is equal to 1. So now we have process A and process B both setting lock equal to 1. And then they both execute their critical sections at the same time. And we end up with a race condition that occurs on the print queue. Dang it. And then they both set lock equal to 0. Dang it. So just using a lock variable and busy waiting. By the way, this is an example of busy waiting. Think about the CPU utilization while this while loop spins, right? We're basically eating CPU going, is lock not equal to 0? Is lock not equal to 0? Is lock not equal to 0? We're doing that over and over again. So that wastes a lot of CPU. So this lock variable is not really a great solution. So how can we do a better job? Well, we can do a better job by getting some support in the hardware for actually doing a lock. All right. And so the way we do that is through something called the test and set lock instruction. So okay, this is a really cool instruction. So let me show you how it works. So the instruction looks like something like this in a CPU. This is an assembly language instruction. So you say TSL, test and set lock, RX, comma, lock. All right, so what this does is it reads the contents of memory location specified by lock. Okay, so like lock is a reference to some chunk of memory. All right, and that chunk of memory has either a 0 or a 1 in it. All right, so let's look inside the computer's memory. So we've got This is the computer's memory, and somewhere in that computer's memory, we have a reference to by lock to this location. All right, the value in this memory is either 0 or 1. We don't know at the moment we do the test and set lock. All right, so the contents of the memory location specified by lock are read, and they are then placed into Rx. All right, so this is part 1, part 2, but there's also a part 3. We're going to write 1 to memory location lock. Okay, so we're going to write a 1 to the memory location specified by lock. So no matter what the value of lock is, when we're done, the memory location specified by lock will have the value of 1 written to it. So there's 3 things that happen when we do the test and set lock. We read the contents into Rx, and we then write a 1 to that location. This happens simultaneously, and it is atomic. This is atomic. So no other process or thread can do this at the same time. All right? Another way to say it is it's mutually exclusive. If process A attempts to start doing a test and set lock at the same time that process B is attempting to do it, only one of those processes is allowed to do it. Same thing with a thread that's running. Only one thread at a time is allowed to do this test and set lock on the memory location that's identified by lock. All right, so what do we do with this? Well, I'm going to show you a little bit of code that could be, we could call this, well, we could call it it could almost be like a method, all right? And so I'm going to show you how the method works. So let's create a method called enter region, all right? So you would call this method in the code up here for process A and process B. We would call this method enter region at the beginning of the critical section of our code. So I'm going to do this. I'm going to grab this code again. It's gotten quite busy. I think maybe I'll just grab the original and then we'll work with that. So I'm going to grab the original up here, copy that, and we'll come down here and I will paste it right here, come over here and just do a little bit of editing to clean this up so you're really clear on where I would use this. Okay. So what we would do is, let's make this just a little bit bigger. It's so cool that I can mess with this. Okay, and it looks like I'm missing C there. Okay, so now what I want to do is just pull this down a little bit so that we're really clear on where our critical section is. Okay, and so what we're going to do, make that this purple, is we're going to call enter region right here. Okay, and if we return from enter region, then we have the lock. We own the lock. All right, and then we're going to have exit region right here. Okay, So now if we return from enter region, we are allowed to execute the code that's our critical section. And then when we're done executing that code, we're going to invoke the method exit region. Now, I haven't written the code for enter region or exit region yet, but that's what we're about to do. So here's the code for enter region. We're going to do the test and set lock instruction, and we're going to read the contents of whatever lock is referring to in the computer's memory into Rx, okay? Now I told you this is mutually exclusive. So if process A tries to do this at the same time as process B, process A may be blocked, or process B will be blocked, but only one of them is allowed to look at the locked variable at a time. So that avoids the situation that we had up here, where we had the possibility of both process A and process B looking at lock simultaneously and then making a conclusion about the value of lock and moving on. That's not going to happen with enter region. Only one process will be allowed to look at the lock at a time. Okay, now remember, in the process of doing this test and set lock, the value referred to by lock will automatically be set to 1. So first we look at it, it could be 0 or 1, and then it is automatically set to 1, all right? Okay, now then what we're going to do is we're going to compare Rx to the value of 0. So if Rx has the value 0, we get the lock, okay? If Rx is 0, we get the lock, all right? And the way we're going to acquire the lock is like this. If we get the lock, it means we get to return from enter region. So if we don't get the lock, jump not equal, what we're saying is if Rx is not equal to 0, then we're just going to jump back to enter region. All right? So what that will do is that will jump us back up to here. And we'll test and set lock again. So we're just going to check the lock. Was the lock value 0? In memory, was the lock value 0? If it wasn't, then go back to enter region and check the lock again. So we're just going to keep checking the lock over and over and over again. Now at some point when we check the lock, it will have the value of 0. If it does, this JNE will fail and we can return from enter region. When we return from enter region, it means that we can then execute the critical section of the code. All right, and then we also have to write the code for exit region. So the code for exit region is really simple. What we're going to do is we're going to move into lock the value of 0. So we're going to move into that memory location in the main memory, the value of 0. So we're basically resetting the lock and saying the lock's available, and then we're going to return. Now only one method at a time can be doing this move, and also this move will be blocked while this test and set lock instruction is executing. So even though lock is a shared resource, we have synchronized access to the lock. Only one person is allowed, only one thread or process is allowed to mess with the lock at a time. You're allowed to look at it and also change its value simultaneously before anyone else can mess with it. So let's try executing this and see what happens. Okay, so I'm gonna grab this. Oops. We'll grab this code. Copy, and we'll paste it down here. Shrink it just a little bit so we can have 2 of these simultaneously. And let's take a look at what happens with process A and process B as they execute with interregion. And what I want to do is just show the value of Rx and show the value of the lock variable in memory. So maybe what I'll do is we'll say star lock. So we're dereferencing lock. So we're looking at this is going to report the value of the lock variable in memory. This is going to report the value of the Rx register. Okay, so let's start out running. So initially the value of the lock variable in memory is going to be 0. We're going to initialize it to 0. All right, so process A and process B run. And let's say at exactly the same time, process A gets a file to print and goes into enter region. And at exactly the same time, process B gets a file to print and enters the enter region. So what's going to happen is even though process A and process B are running at exactly the same time on the computer, one of the two processes is going to get to execute this test and set lock instruction first. All right. And the moment that happens, let's say it's process A. So the moment process A gets to execute TSL, before process B executes TSL, what happens is when process B attempts to execute its TSL, it gets blocked. All right. So process A gets to run the TSL instruction. And let's do this. I feel like it would really even be helpful to have this enter region code twice as well. Okay. All right. So, because I want to just sort of check off what's happening. So process A gets to do its TSL instruction before process B. But while process A is running its TSL instruction, process B starts to execute its TSL, but it is going to be blocked. So I'm going to write that, blocked. All right. So process A says, look at the lock variable. And remember, I guess we'll have the Rx for process A over here, the Rx for process B over here, and we'll have star lock right here. Okay. So initially lock is 0. All right. So process A executes the TSL instruction. So the TSL instruction is going to copy lock into Rx. So Rx is going to get the value of 0. But at the same time, it's going to change the value of lock from 0 to 1. All right? Now, as soon as the TSL instruction finishes executing, it unblocks process B. So process B is now allowed to run the TSL instruction. So what process B is going to do is copy the value of the lock variable into its Rx. So that's going to get copied. What goes here? 1. We're copying the 1 that's now in the lock variable. Okay, so now let's go back to process A. Process A does a comparison. Is Rx equal to the value of 0? Well, yes, it is. It is equal. And so process A then says, well, if it's not equal, I'm going to jump back to enter region. Well, it is equal, so we're going to skip this, and then we're going to return. When we return, we now allow process A to execute the code in its critical section. All right, let's go to process B. Process B just executed the test and set lock instruction, and determine that Rx has the value of 1. When it goes to execute this comparison, compare Rx pound 0, or compare Rx to 0, that is going to return false. Rx is not 0, it's 1. So when it hits the jump not equal to enter region, it's going to say, okay, Rx wasn't equal to 0, so we are going to jump back to this test and set lock instruction. All right? And it's going to repeat this over and over and over and over again, spinning between these three statements while process A is executing its critical section. When process A finishes executing its critical section, it's going to execute exit region, and exit region is going to reset the value of the lock variable in memory to 0. Right? As soon as it resets the value of the lock variable to 0, let's show that happening here. The 1 goes to 0 on exit region here. As soon as that happens, the test and set lock instruction for process B will execute. Lock will get copied into Rx, and Rx will have the value of 0. When this comparison operator gets executed, it's going to return true, that it is equal. And this jump not equal will fail, and we will return. And now we're going to return from enter region, and now process B will be able to execute its critical section. So I hope all of that makes sense. And you can see how process A and process B can execute some code concurrently, but when one process is able to get into enter region and return, the other process is going to be blocked. This enter region will not return while the code in this critical section is executing. And of course, it could happen the other way. Process B could be the one that gets into enter region first, then process A tries to go into enter region and won't return. It'll busy wait until process B returns from enter region and executes its critical section.